Hi, I'm Tom Hayes, and I'll be presenting Wake Up and Join Me, an energy-efficient algorithm for maximal matching in radio networks. This is joint work with Varsha Dani, who just started a faculty position at RIT, my student Ayush Gupta at UNM, and Seth Petty at UMich. Our motivation comes from large networks of low-cost sensors equipped with radio transceivers. These are typically deployed in remote and hazardous terrain so that the network topology is initially unknown and arbitrary. One of our primary concerns is battery life and energy use. For this, the radio communication can be a dominant cost. And we note that as device sizes scale down, the cost of listening for signals is comparable to the cost of transmission. Here is our model of a radio network. We start with a graph on n nodes, each representing a processor. We will work in discrete time, where at each time step, a node must choose whether to sleep, which is free, to send a message of up to log n bits, or to listen. Sending and listening both cost one energy. When a node listens and exactly one neighbor sends, the sent message is received. However, if a node listens and any other number of neighbors send, no message is received. All nodes start out identical and share common upper bounds on the number of nodes, small n, and the maximum degree, delta. The goal is to solve some distributed computational task in polynomial time and polylog energy. Specifically, as the title of the talk suggests, we are interested in finding matchings. A matching is a pairing between nodes, which is one-to-one. No two nodes may share the same partner. We say a matching is maximum if the number of pairs is as large as possible, that is, a global maximum. We say a matching is maximal if no pair can be added without first breaking up an existing pair, that is, a local maximum. It is well known that every maximal matching is a 2 approximation to maximum matching. There are efficient centralized algorithms for both problems, notably an easy greedy algorithm for maximal matching, and various augmented paths algorithms for maximum matching. We begin with a quick review of the centralized greedy matching algorithm. Starting from an empty matching, we greedily add as many disjoint edges as we can. This always succeeds and runs in linear time. Next, we consider a parallel distributed version of this algorithm. Now we take the perspective of a single node. We try random neighbors one by one until we find one that is unmatched, at which point we make an edge with it. Now the good news is that this results in a maximal matching, and we also get a good parallel speedup. The bad news is threefold. First, this isn't a radio broadcast algorithm. We have point-to-point communication between nodes. Second, the energy usage for this algorithm is as bad as it can be for such a fast algorithm. And third, any unmatched nodes end up paying a high energy cost because they never figure out when they should quit. Here's a rough sketch of our radio algorithm. It is based on a simple 3-step handshake. In each round, we randomly choose one of 3 roles: sender, listener, or sleeper. Senders transmit in time step 1. Any listener who hears responds in time step 2. And if the sender hears the response, she sends a confirmation in time step 3. We note that intuitively, if we are sharing our radio channel with d other players, we want to sleep 1 minus 1 over d of the time, and only participate as a sender or a listener about a 1 over d fraction of the time. However, there are some issues here. First off, we don't know the degree d, which is our current number of unpaired neighbors. Secondly, my degree might be very different from my neighbor's degrees, and their neighbors' degrees, and so on. This will be an issue because I need to both transmit and receive in our three-step handshake protocol. So which degree do I use? My degree or my neighbor's degree? Finally, there isn't really a single channel in any case, since it is radio broadcast, which means that every message I send goes into a separate receive channel for each of my neighbors. The good news is that the maximum degree delta is always an upper bound on D. Well, one secret is to use the formula on this slide to decide how often to participate. So at times in round T, we send or listen with probability 1 over quantity delta minus T over log n. This function slowly grows from an initial 1 over delta up to 1. At the same time, our degree may decrease due to our neighbors getting paired up. However, eventually, our participation probability hits the sweet spot of 1 over d and stays there long enough that we will almost surely get paired up. This is assuming that our neighbors don't all get paired up before that, but that still results in a maximal matching because if no one is left for us to be paired with, then we don't have to be paired. Let's step through an example. We start out with all the nodes asleep. In each round, the nodes toss coins to decide whether to send, listen, or sleep. No progress can be made unless a listener is next to a sender. So here, the listener is not adjacent to the sender, so no message is received. In this picture, I have a listener next to two senders. Their signals interfere with each other, causing a collision, which means that the listener can't hear anything. In this step, the signal from the sender is successfully heard by two listeners, who then both send a response, but those responses collide, which means that the handshake will not succeed. Note that since no confirmation will be sent in the third step, the listeners will not erroneously consider themselves to have formed an edge with the sender. The ideal situation occurs when exactly one sender is next to exactly one listener. In this case, all three messages go through without interference. And both nodes realize that an edge has been formed, at which point they go to sleep for the rest of the game. And so on. So in summary, with the right participation schedule, our three-step handshake protocol finds a maximal matching in time that is big O of the degree times log n, maximum degree times log n, and log squared energy. So here we assume the maximum degree delta is known in advance. But of course, the total number of nodes n is also an upper bound on the maximum degree. One application of our work is to the related problem that we call neighbor assignment functions. So suppose that we want to map every vertex in the graph to exactly one of its neighbors. for instance, to act as a backup device. We define load as the number of neighbors that have been mapped to a single node. And suppose that our goal is to find an assignment of every node to one of its neighbors, which minimizes the maximum load. One result is that the minimum possible maximum load turns out to be something called the matching cover number. That is the smallest number of matchings that would cover all vertices of the graph. And our next result is that it's possible to log and approximate the minimum load neighbor assignment function using only polylog energy. And the key idea in our algorithm for this is to inductively build up the assignment function using maximal matchings. And after each maximal matching, you build a residual graph centered around the nodes that haven't yet been assigned. So that's the talk. We only know a very few very basic results in this model, which means there's lots of room for further progress. And I will leave you with some open questions. First would be to design time and energy efficient algorithms for other important network tasks, such as routing, coloring, leader election, and, for instance, preference aggregation. But there are many more. Another direction we think is interesting is to try to make the algorithms more robust against failures. For instance, can we make a distributed radio algorithm which can deal with nodes failing during the algorithm and dropping out? Or can we handle nodes entering the network in the middle of the algorithm? Our model assumes what is essentially a global clock, which keeps all of the time steps synchronized across nodes. Can we get rid of that? So what if some nodes started a few steps late? Right now, our algorithm is not particularly robust to problems of that sort. And one more example is, what about Byzantine faults, where some of the nodes start running adversarial code, presumably trying to disrupt the algorithm that we've written. In this case, the limited battery life could actually help us because it will place at least some restriction on the extent to which these Byzantine or hacked nodes could disrupt the functioning of our algorithm. Thank you.